GPT-4 is already having quite some impact on how software is being developed, and I thought I'd put GPT-4 to a little test to get a feel for its power. I learn best from concrete examples, so I've settled on the task of improving a little assembler I had written in Python for my DIY Minimal 64 home computer, a system unknown to GPT-4. And I love compact Python code. Well, to a point where others, including maybe GPT-4, may say my code is becoming unreadable. It might just be me, but I can understand code best if it fits on a single page. My handwritten assembler only had 120 lines of code and already was as concise as I could make it. Now, with extensive help of GPT-4 and to its rescue often against its explicit suggestions, I have condensed my code down to only 60 lines. I think that sounds pretty inviting if you want to learn how assemblers work. Even when used somewhat against its grain, GPT-4 is incredibly fun and helpful and provided me with many bug fixes, ideas and new insights I wouldn't have found otherwise. Quite a humbling experience. I still had to deliver the specific logical code structure I wanted, but GPT-4 helped me improve on the details so much. Now this 60-line assembler is so tiny that it becomes almost pointless to explain it. We can directly look at the code. Or even better, let's GPT-4 do the job. This is a deliberately tiny assembler for a DIY CPU system. Could you please provide a concise description of the overall program structure? So that's kinda nice, isn't it? No more tears with documentations. Now let's challenge GPT-4 a bit more by asking it to compare my implementation to the abstract definition of my assembly language written in EBNF, that is, Enhanced Bacchus-Naur form. Point out potential inconsistencies and rate the overall quality of the Python code and EBNF on a scale between 0 and 100. The Python code is generally well structured and does a good job of implementing the assembler. However, it lacks proper commenting, and some parts of the code are a bit difficult to understand without context. Fair enough, I'd say. The EBNF is mostly well structured and covers most of the assembler syntax. However, there are some inconsistencies and areas for improvement, as mentioned above. It comes up with a couple of points here that I'm not so sure about. Let's ask. Okay, so dialogue is important to focus GPT-4's attention onto certain aspects. I take away that GPT-4's capacity to deeply understand complex structures is still limited. Tasks should ideally be broken down into smaller chunks, and it's important to not blindly follow suggestions. But hey, it's a language model, not even specialized for programming. I'm impressed. Now let's do a quick code review and, of course, use the assembler. Before diving into its two-pass structure, it's important to understand the global state of the assembler and the findElement function. The first line creates an array of mnemonics by splitting a contiguous string. The assembler maintains a global state that includes variables for the loaded source code, src, program counter, PC, the current position in the source code, EP, the line number, and a dictionary of labels. I'm also importing a hex file module for Intel hex output. That was a helpful suggestion by GPT-4 since I was unaware of that package. The findElement function plays a crucial role in iterating over the source code. It counts lines, skips white spaces and comments, and returns the length of the current element. It helps the assembler navigate through the source code efficiently and identify relevant elements. I find GPT-4 really helpful with these smaller tasks, for example, sorting out these regex expressions here. I usually struggle with this notation and tend to forget what I've learned pretty quickly. Can you briefly explain the regex without going into all details? In summary, this regex pattern matches sequences of white spaces and/or commas or comments that start with a semicolon and continue until the end of the line or a null character is found. Again, I'm impressed. Anyway, with this context in mind, let's proceed to discuss the two-pass structure of this assembler, where pass 1 focuses on storing label definitions and their program counters, and pass 2 handles code emission. In the first pass, it reads through the source code, skipping white spaces and comments, storing label definitions and their program counter values. During this pass, it also takes into account the preprocessor command org to set the program counter. In the second pass, the assembler emits the machine code. It processes each element in the source code, translating mnemonics, expressions, and strings. Expressions allow for a combination of hex values, decimal values, and labels. Once the second pass is complete, the assembler outputs the general machine code in Intel hex format, which can be loaded into the Minimal64 home computer. Okay, let's try that using this assembler program I've written. It's just about 900 lines of code. As you can see, the assembler produces a clean Intel hex file output, which we can copy and paste into the Minimal64 home computer. I type receive and paste the clipboard data as serial input. Let's run the code. And here you have it. Space Invaders in machine language, assembled by 60 lines of Python code. If you haven't seen my previous video about the Minimal64 and its emulator, I'll put links to it in the description. I have also ported the assembler to run natively on the Minimal64 hardware. And with the concise Python code at hand, that was a relatively straightforward task. As an example, let's assemble the source of my Tetris clone. With its 420 lines of code, this is not a toy example. Okay, that's all looking pretty good. And here we have Tetris again. I hope you found this as interesting and fascinating as I did. A big shout out to the fantastic people at OpenAI. Keep up the great work and take care. Bye.